Hi, welcome to this video. Today we are looking at an assignment problem, one of the optimization techniques that is covered in operational research. We want to see how unique it is from the other techniques of operation research. We basically want to look at definition or description of an assignment problem. Then we shall have some few examples to illustrate applicability of an assignment problem. Then we shall also look at the characteristics behind characteristics or features of an assignment problem. And finally, most importantly, we shall look at how then do we solve an assignment problem. And we shall be looking at particularly one particular technique of solving an assignment problem, and that's the Hungarian technique. And that is what we are going to be discussing in this particular session. Now, an assignment problem is treated as just a special kind of transportation problem where the objective is to assign a number of resources to an equal number of activities with the intention of minimizing either the total cost, time, distance, and so on, or maximize the total profit. Remember, it's an optimization. If you remember what we are looking at in transportation problem when you're laying out, we said that transportation problems are two-way table, having sources on one end and destinations on the other end. Now, the sources in assignment problem are now replaced with the resources, and then the destinations now here are now replaced with activities. So the activities could be called also tasks, or actually just jobs. And resources here could be subjects or personnel, could be men, could be machines, and so on. And so an assignment problem is also a two-way table. And we are going to have cells inside here, where let's say cell C11, C12, C13, and so on. C21, C22, C23. Let me assume like maybe we have 3 activities and 3 subjects, 3-1, C32, and C33. So one thing we mentioned and we emphasize so much in under transportation problem was that the main objective in transportation problem was more or less minimizing the cost, minimizing the cost of transporting goods from various sources to destinations. It's the same thing in assignment problem. We are going to see more of minimization problems, and this could still be cost, could still be a function that is our interest or could be the objective. But then it can also be even time. It could be also minimizing time. This could be even distance and so on. But then we can also have an objective function where the interest is now to actually maximize maybe a particular output. This cost could still be interchanged with profits, so that then if there are profits, then we are looking at how we can assign various resources to various tasks in a way that we're able to maximize profits, or in a way that we're able to maximize the revenue collected, if it's an institution or an organization. So it is an optimization and can take the form of minimization or maximization for that matter. Why we are saying an assignment problem is very important is because we are saying that resources, like for example, if we are having personnel, 2 of us can perform 2 tasks equally well. But when you look at each one of us, one could be more efficient at one activity or at one task than the other. And because of those inefficiencies, assignment problem comes in by giving us a better way of assigning subjects to particular tasks in such a way that the total time taken or the total costs incurred or that is actually as minimal as possible, or loss is actually minimized as much as can. If it's profit, is actually maximized as much as we can. Maybe take you through 3 illustrations that make assignment problem to be a worthy technique to explore. When you look at this particular example 1, It's talking about the Ministry of Sports, which has decided to carry out renovations of 5 main stadiums in the country before AFCON in 2027. Our 5 contractors have submitted quotations. And then we are told it is a policy of the ministry to award not more than one contract to a contractor. So if the objective of the ministry is to minimize the cost, how should they award the contract and how much expenditure should be budgeted? So when you look at this, one thing under assignment problem I need to emphasize is that those resources or subjects, each one of them will be assigned only a single task at a time. So we are talking of one-to-one matching. So we are having resources here, which are the contractors. So these are now the resources, and the activities or tasks are actually now the renovation of those stadiums. And we have 5 of them. You can see the number of tasks is actually equal to the number of contractors. So there are 5 contractors and there are 5 stadiums. And you can see they are talking of minimizing the cost. That means whatever is inside these cells now this time round is not representing time or whatever, but is representing cost. And the intention of the ministry is to minimize the total cost in renovating all these 5 stadiums. So they will want to have a way, like, for example, contractor 1 requires maybe this could be maybe $18,000, maybe to renovate that stadium 1. But the same stadium 1 contractor 2 has quoted $17,000. And I think the lowest contractor 5 has quoted about maybe $1,000, if these are in $1,000 for that matter. You can see those variations. And so you in the ministry now, or in charge in the ministry, you wish to assign in such a way that you get, at the end of the day, the ministry spends less. Otherwise, if there are many stadiums and many contractors, even 5, the way it is a 5 by 5 kind of table, it is not easy to assign manually. For instance, if you are to assign Stadium 1, you'll say Stadium 1, I should assign somebody that has quoted the lowest, let's say the lowest figure. And doesn't necessarily mean anyway that the lowest figure, the one who has quoted the lowest figure will do the efficient work. Of course, that's not subject to this discussion. You may award that, but then when you look at Stadium 2, the lowest contractor who has quoted a smaller figure is contractor 2. When you look at Stadium 3, you can see again contractor 2 has quoted the lowest, and you can't assign contractor 2 to renovate Stadium 2 and Stadium 3. That would be wrong. And because of this kind of similarity, you'll get to challenges now when you move along. You can get a scenario where maybe a particular contractor is the one maybe conspicuously appearing to be the one quoting the lowest figure across. And so that's why we now need a better technique of assigning these contractors to the tasks so that we are able to minimize in total our cost, like is our interest in this case. So this is a good scenario or a good problem where now assignment problem comes in, where the objective is to minimize the cost. Another example which involves not necessarily cost is maybe an automobile dealer who wish to assign men to 5 different jobs. So we have 5 men. So those are now the resources. And then we have jobs or tasks here. So there are 5 jobs to be done. And one thing, of course, the 5 men, each one of them can actually do the 5 given jobs. But then, of course, when you look at the efficiencies, like the first man can do job A in 11 hours. The second one can do the same job in 9 hours. And you can see there is even one who can take 21 hours. The fourth man can take 21 hours to do the same job. Again, you can see, let's say, job D, the first man can take 16 hours. The second man can take 6 hours. And then there is a man, the fourth man, who can do the same job in 28 hours. It's because of these inefficiencies that now we require at least a formal technique that can help us assign these men to all those tasks in such a way that we are able to, in this case, to minimize the number of hours needed to accomplish all these 5 tasks. So we are going to assign each individual a particular single task, but then at the end of the day, we are able to get that time. So this is a good example again of an assignment problem where the cells now represent time and not cost like the previous example. But then the objective is actually again one that requires us to minimize that time. Our last example is one where we are talking of a banker who has employed 3 cashiers, or I may call them tellers, and they are performing 3 tasks or customer services. So there is customer service 1, customer service 2, customer service 3. Each one of them should have its own counter. And then the cashiers now, they have A, B, and C. This could be their names, or they could be identification names in the facility. So, however, you can see that they take different time duration to serve customers. For instance, customer A takes 20 minutes. The time is actually in minutes. This is an average time, 20 minutes on average, to perform this task 1. Let's say task 1 is actually just dealing with these are teller dealing with the deposits and withdrawals. Customers who come in to do withdrawals and deposits. Counter 2, let's say we are talking of somebody who is just registering new members with bank accounts. And customer, this third function on counter 3 could be maybe dealing with customers who are coming in either to inquire on loans. And so we can see cashier A can take 20 on average minutes to on average to carry out that exercise of a customer has come in either to do a deposit or to do a withdrawal, on average 20 minutes. But then cashier B on average from experience and his expertise or high expertise takes slightly lower minutes, 17 minutes. Cashier C takes 18 minutes to do that same function. But when you look at counter B, where we are dealing with the registration of accounts to new members, cashier A seems to be more efficient, takes about 15 minutes on average. Cashier B takes 16 minutes, and cashier C takes 19 minutes. In terms of loans, you find that it is cashier C who is even super, takes slightly lower, 27 minutes. Cashier B takes 33, and cashier A takes 31 minutes. And so you want to assign these cashiers to these counters with different functions, such a way that one cashier is performing one only function. But at the end of the day, in this particular case, again, we want to minimize the time spent to offer these services to the customers, the total time spent to offer these particular 3 services to the customers. And so this becomes an assignment problem. Different from now a transportation problem where we are talking of just goods being transported from one end to another, and our interest was just to minimize the cost of transportation. Now, having known now areas where areas or examples where we can actually apply assignment problem, we draw 3 characteristics from this. One of them is that the resources to be assigned and the tasks are known and finite in nature. Yes, you must at least know how many resources or how many cashiers, for example, how many cashiers do you have and how many functions or tasks do you want them to perform. So they must be known in advance. One thing you are realizing the assignment problem is that the number of resources is always equal to the number of tasks. It's a square. And so when it's equal, in that case, we talk of a balanced assignment problem, just like we are talking of a balanced transportation problem where we had the demand and the total supply actually being equal. Here we are talking of the number of resources being equal to the number of tasks, or the number of subjects being equal to the number of jobs. Then we talk of a balanced assignment problem. And so just like we are dealing in transportation problem, in the event that the two are not at balance, then you need to create either dummy row or a dummy column before you proceed. And so we are saying then this number of subjects and number of tasks must be known in advance for you to actually say you are dealing with an assignment problem. So it must be a finite number of tasks and a finite number of resources. We're also saying that the resources are assigned one-to-one basis. I think this one I've emphasized. I said here that if we are looking at this case of a bank setup, we want at the end of the day, we have cashier A only assigned either to counter 1, and cashier B may be assigned to counter 2, and cashier C assigned to maybe counter 3. We're not going to have a single individual being assigned more than one task. It's a one-to-one matching problem. And then we are also saying that the outcome of each assignment must be expressed quantitatively in terms of payoffs or revenue, profit, cost, time, distance, etc. Yes, and that is very clear in an assignment table. You can see those figures are the ones that are guiding us. Those are the quantitative numbers. They are quantitative numbers. They have expressed that B can maybe complete this task in this particular number of times. So we are not seeing blanks. There's no cell which is blank. So all of them have figures and they are quantitative numbers that we are going to use. And so that must always be done or complete for us to move on with an assignment problem. So that's basically a good, precise description of an assignment problem, how different and how unique it is just from the general transportation problem. Now, because the transportation is an optimization technique, there are ways of solving or optimizing that technique. The literature will find there are these several techniques, among others, the complete enumeration, the simplex, the transportation, and the Hungarian. Because we are saying transportation because it being a special kind of transportation table, one may want to think that probably we can also explore the modified distribution method as stepping stone method to see how we can use it in solving an assignment problem. However, the Hungarian method is thought to be one of the easiest and simplest method in solving assignment problems. And so it has been widely used in the literature. And that is why we have also focused on it in this particular session. So I take you through the steps of solving an assignment problem using Hungarian method. And then we can illustrate those steps with a practical example. So the steps are about 6. The first one, we form an assignment table. And an assignment table is what we have just mentioned, having rows where you have specified the resources or the subjects, and then having columns where you have specified the tasks or jobs, and of course, having complete filled up cells here, which could be time, or could be distance, could be cost, and so on. And so simply a table, a two-way table with the tasks and resources is an assignment table. But most often the problems you'll be having, they've already have created for you this table. So you will not be performing this step most often. Like even the illustrations we have just had, the tables were already there. So you only proceed to step 2, where you carry out the row and column reduction. I'll be explaining briefly what that involves. And then after doing row and column reduction, you construct vertical and horizontal lines. But as you construct, you seek to construct the minimum number possible. The minimum number possible to cover all zeros in the table. After the column and row reduction, you'll have some cells having zeros. So you'll be seeking to cover those zeros using horizontal and vertical lines. Once you have covered, you test for optimality. And the test here is check whether this minimum number of lines you have drawn is actually equal to the number of assignments. If that is true, then you say the optimal solution has been reached, and the table you have is actually the final one. But in the event that the minimum number of lines you have drawn does not match with the number of assignments of the problem at hand, then it means you need to proceed further. You can do improvement, and you do this by identifying the minimum value among all the elements that are not covered by a line. And then the value you have identified as the minimum, you subtract it from each element not covered by a line, but then you add it to you add that value to each of the elements with intersecting lines. We are going to do that, and then you repeat these two steps of constructing horizontal and vertical lines and testing for optimality until you get you reach an optimal solution, or you get the final table. Once you have gotten the final table, you extract the optimal solution from the last table by identifying unique zeros. Let's go straight to an example so that then we can use an example to be able to understand these steps clearly. So we have an example here which is talking of an ICT company that has 4 employees or technicians. And these 4 technicians are different locations in the county. Their role is to maintain networks in the premises of their various customers. And so we have 4 maintenance requests that have been received from the 4 customers. And the technicians are available to serve. Whatever we have in the cells is the distance in kilometers of each of the technicians away from the various customer premises. So like technician 1 is 19 kilometers away from customer 1 premise. He is 23 kilometers away from customer 2 premise, and 16 kilometers, 25 kilometers accordingly from the other premises. And so it is to the other technicians. So you're having here now, this is distance in kilometers. And so you can easily see from the end, the company here has interests to see how they can actually minimize the total distance these technicians cover in totality to offer the services or to reach out to the customers and the various premises. And so the question now below it says, determine the optimal assignment of the technicians to the customer premises that will minimize the total distance covered. You can see now the objective here is to minimize the total distance covered. So already we have the assignment table. So we begin by constructing what I've said, the column and row reduction. And so if we begin with the row reduction process, this is the same assignment table. The row reduction process simply requires that we first of all identify the minimum value in each row. When you check row 1, the minimum value 19, 23, 16, and 25 is actually 16. The second row, the minimum value between 15, when you look at 15, 21, 20, and 22 is actually 15. And then the third row is 17. The fourth row is 14. Those are the minimum distances or minimum values in each row. So what we need to do, we now, like for example, in row 1, I now subtract 16 from 19. So I take 19 minus 16 to get a 3, 23 minus 16, get 7, 16 minus 16 are 0, 25 minus 16 to get a 9. Then the second row will be doing 15 minus 15 to get a 0, 21 minus 15 to get a 6, 20 minus 15 to get a 5, and then 22 minus 15 to get a 7. We do that to the other rows, and we get now a table where we have subtracted those values, a table looking like this. You can see the zeros have started emerging now and appearing in our table. So that way I've done row reduction. So row reduction is just, in this case, because we are dealing with a minimization problem, a problem that requires us to minimize the objective function. We select the minimum value in each row and we subtract from the corresponding elements in that row. Now, the next thing we need to do now, we carry out now again column reduction. And column reduction now, I'm going to identify again the minimum value in each column. So the minimum here is 0. The minimum in the second column here is 1. The minimum in the third column is 0. Minimum here is 4. And so once you have done that, you're able to get a column of this kind where you have identified the minimum scores. Then again, you subtract these minimum values from the corresponding values in that column. Now, columns with zeros, if you subtract 3 minus 0, 0 minus 0, 5 minus 0, they remain unchanged. The values remain unchanged. So column 1 and column 3, because the minimum values are zeros, the values will not change after column reduction. But then in column 2, they will change because this will be 7 minus 1 to be 6, 6 minus 1, 5, this will be 0, this will be 9. Then this one will be 9 minus 4 to be 5, then 3, then 0, and then 4. And so you get a table where you have done both column and row reduction, a table appearing like this, where we have now, you can see zeros are now appearing almost everywhere. So once you have done now this column and row reduction, and by the way, it's not a must that when you're doing the column row reduction, you begin with the row first, then come to column reduction. You can also begin with the column reduction process, then come to row reduction process. You'll eventually come to this same result in the cells or the final table. So irrespective of whether you have begun with rows or you have begun with columns, the end result is the same. So it is at this stage now that you now begin drawing lines to cover all zeros. Ideally, you can see a 0 is appearing in every column or in every row. So if I'm drawing, and these lines have to be horizontal lines or vertical lines. So you can see I can draw even just those. Those are already 4 zeros. I mean, those are 4 lines and they have covered also 4 zeros. So I'll be able to have lines that are 4. Still okay. I can also draw the lines instead of drawing the vertical one. Instead of drawing horizontal ones, I can also draw vertical ones just this way. Zeros are actually or cross. I'll still end up with just, I'll still have covered all zeros. I can also do a blend instead of just having vertical lines only. It can also be a blend of maybe just 2 vertical and 2 horizontal. I'll still have covered all the zeros. But the logic here is we draw the lines. It's not just drawing the lines for the sake of drawing. We have to draw in such a way that the number, we minimize the number of lines we have drawn. So we want to draw as fewer lines as much as we can to cover all the zeros. So if there is a way we can draw fewer lines, the better. And you can see here, one way of drawing fewer lines, one line cannot cover all the zeros in this, because one line cannot cover. Similarly, 2 lines may also not cover, but you can have 3 lines. This one, a line covering most zeros in that. Then I can have this, and I can have that. When I do this way, I'll have covered all the zeros in the table, but I've used a lesser number of lines. At least I have 3 lines only, because I've covered all the zeros in the entire design. And so this is actually the minimum number. There is no lower number of lines you can draw. So the minimum number of lines here I've drawn is actually 4. These are 4. Actually, these are 3, sorry. There are actually 3 lines I've managed to draw. Now you check this minimum number of lines you have drawn against the assignments. We are supposed to do 4 assignments here. There are 4 technicians against 4 customers. So we are supposed to have 4 assignments. Technician 1 assigned to a customer, technician 2 assigned to another customer. So 4 sets of assignments. So you can see the number of assignments are actually 4. But the minimum number of lines we have drawn is 3. So we all can see that actually the minimum number of lines is not equal to the number of assignments. And so that means that the table we are having is actually not the last one. It's not yet optimal. we can still improve it. And so how do we improve it now? Now in improving, we now check in this entire table, we check the elements that the line has not gone through. Like this element, a line has not gone through, this one, a line has not gone through, a line has not gone through, a line hasn't gone through, a line hasn't gone through, a line hasn't gone through. And so those becomes the elements that we are of interest in. And so from those 6, we check which one is the lowest or the minimum. So 6, 5, 9, 5, 3, and 4. 3 is actually the minimum value. So 3 is actually the minimum. So once you have identified the minimum value among the values where the lines have not gone through, this minimum value, we subtract it from these elements that didn't have the line going through. We subtract that 3 from it, that particular value you have identified. We subtract it from there. So that now, the new table where we are going to now formulate will now have here, will now have this cell 1, 2, will now have a value of 3. This one will have a value of 2. This one will have a value of 6. This one will have a value of 2. This one will have a value of 0. And this one will have a value of 1. Now, after subtracting that 3 from those other values that did not get a chance for a line to go through, we check now the points of intersections. The points of intersections. The points of intersection of the lines. This line, the lines are intersecting at those 2 points. Now, at the point of intersection, we are supposed now to add. So that 3 we have been subtracting from those, we now add it here at the point of intersection. We add. Remember, this is 5, so plus 3, it is now coming out to 8. And this will now be 3, because it was 0 plus 3. Now, these other elements now, where the line is just going through once, you leave them the way they are. So we now want to have a new table where we have done these adjustments, where we have subtracted values, particularly this column 2 and column 4, where values have totally changed, 3, 2, 0, 6, and now 2, 0, 0, 1. And then we can see also row 3, we have also changed some values because of lines intersecting there. So the new assignment table will now appear this way. You can see the cells I've written in red are the cells which have had their values change. So this will be now our new table that we shall try now to again test for its optimality. And we begin by, first of all, again drawing another set of horizontal and vertical lines to check the minimum possible number of lines, whether they actually tally with the number of assignments. And so we again, I'll go ahead. We can draw lines. Now, if you look at this problem keenly, you can only draw 4 lines to cover 4 zeros, to cover all the zeros in the entire design. You can have this way, but you'll still be needed to have that. So the minimum number of lines now we are able to draw is actually 4. And the number of assignments, we say they are also 4. So we have gotten to a scenario where the minimum number of lines, the vertical and horizontal lines that cover all the zeros in the design, actually tally with the number of assignments of the problem. And so in this case, we say that the table we have is actually the final table. And so we cannot go further than that. We need to use it and now do our assignment so that we are able to identify which technician is assigned which particular customer. And so those are the comments I've actually written here, that in this case, the minimum number of lines that cover the zeros are 4, and they're actually matching with the number of possible assignments. Hence, this table is final and provides the optimal assignment. So the next step then that we follow is now to identify the unique zeros. So I pick that table again, and so we try now to identify the unique zeros. These unique zeros are the ones that are going to help us identify which technician goes to which technician. So first of all, begin identifying a zero that is unique both in a row and in a column at the same time. A zero that is unique both in a row and a column at the same time. When you check in there is this only zero that is unique, both in column 3 and in row 1. There is no another zero in row 1, and there is no another zero in column 3. So we mark it because it's an important one. Then, so that means we are saying that technician 1 eventually will have to be assigned to that particular customer, because that's the only unique zero. These unique zeros are helping us to identify the customers. And then now, when you check again, there is no unique zero in a column and a row, but there is a unique zero in a column. Like this zero is actually unique in column 2. Column 2 doesn't have another zero. And so that means that because when you check the other columns, column 1 has 2 zeros, column 4 has 2 zeros, but this column 2 has a single zero. So that means we are saying that technician 3 will actually provide his services to customer 2. Well, there's no, that unique zero tells us where assignment is. Now, if technician 3 will give his services or her services to customer 2, then it means there is no way technician 3 will again be assigned to customer 4. So that will be an X. There's no way it will be assigned to customer 4. So that will mean, therefore, that customer 4, if we have crossed this zero, it means customer 4 has now this only zero that has to serve him or her, has only that single zero that has to serve him. And so that means you're saying, therefore, that customer 2 will just have to come and serve customer 4, because once you have crossed this zero down there in column 4, the only remaining zero that should serve customer 4 is that. That means technician 2 will be assigned to customer 4. Now, when you look at that, if technician 2 is assigned to customer 4, you'll again agree with me that therefore, there is no way technician 2 will be assigned to customer 1 again, because we are saying one technician, one task. And so that means that this other zero will remain now for customer 1, and therefore technician 4 will actually provide services to customer 1. And so this now helps us now to know who serves who and who serves who. So that way you can now calculate the optimal assignment by calculating distances. And to calculate distances, now we go back, because remember, the table that we had initially, the original table of technician against the customer, that assignment table, the cells were consisting of distances in kilometers before we began the column and row reduction process. So we need to go and check how far technician 1 is from customer 3, how far technician 2 is from customer 4, and how far technician 3 is from customer 2, and how far technician 4 is from customer 1, so that then we can be able to get the total distance that has to be covered by all the technicians to be able to provide the services that the customers at their premises need. And so when we do that now, we go back to the original table to check how far technician 1 is from customer 4. We now go back to the original table where we had before beginning the reductions. You find that technician 1 was actually 16 kilometers away from technician 1, and technician 2 was actually 22 kilometers away, and technician 3 was 18 kilometers away from customer 2, and technician 4 was actually 14 kilometers away. So we sum 16 plus 22 plus 18 plus 15 to give us now the total distance that has to be covered by all the technicians to be able to realize the total distance covered. And so we report as a conclusion that the optimal assignment that minimizes distance is therefore technician 1 assigned to customer 3, 16 kilometers away, technician 2 assigned to customer 4, 22 kilometers away, technician 3 assigned to customer 2, 18 kilometers away, and technician 4 assigned to customer 1, 14 kilometers away. When you sum all this gives us 70 kilometers, and that will be the total distance covered. So that's how now you apply Hungarian method in solving an assignment problem that is of minimization kind. Two important remarks we need to remember. The first one, I've already mentioned it, that if we can, that during the row column reduction, we can either start with the rows, finish with columns, or we can begin with columns and finish with rows. The results is the same, there's no problem. And the second remark, we are saying that the problem we have done, and most problems we'll be doing will be, of course, be minimization kind. But should we get a problem of maximization kind where the sales are now maybe talking of revenue or profits to be maximized by assigning some subjects to some tasks, then in this particular case, you now not be identifying the minimum during the row column reduction, but you'll be identifying the maximum value in each column or in each row. Then you are subtracting the value from each of the elements in that corresponding column or row. So it will be now like the reverse kind of process. Thank you.